So how do computers modify numbers, such as adding, subtracting, multiplying, etc.? A computer that didn't have these abilities wouldn't be very useful. It would be like owning a calculator that you could only enter numbers into and nothing else. Classically, the part of the computer responsible for these operations is called the Arithmetic Logic Unit, or ALU. In this video, we'll be looking over how an ALU operates and how it integrates into a computer. We'll be looking at the ALU for a minimalist 8-bit computer that I designed using discrete components called the TCPU 816. The reason being that the ALU in this computer is just about as simple as it can possibly be in terms of hardware, while still remaining reasonably functional. In fact, this ALU is technically only able to perform addition and not AND instructions in hardware. Despite this, the computer can still perform subtraction, multiplication, division, and any logical operation. But before we dive into how an ALU is able to accomplish this, let's first start by reviewing how computers add and subtract. So this right here is an example of a 1-bit adder. This takes two 1-bit values and returns a result. So on this side we have our inputs A and B, and on the other side we have our outputs. And right now we have 0 plus 0, so we have the result of 0. If on the other hand we have 1 plus 0, we have the result of 1 in the sum. The same is true if we set B to 1 and A to 0. It's 0 plus 1, which equals 1. But what happens if both bits are on, both A and B? Our issue is that this is a 1-bit adder. It can't count to 2. So what it'll do instead is it'll do 1 plus 1 equals 0 for the sum, but it's also setting the carry high. And what carry does is it tells whatever is attached to it that whatever value it's trying to add overflows what it's capable of adding. But in order to take advantage of this carry flag, we have to modify our adder so it will also accept a carry. So this adder, which would be previously referred to as a half adder, is now a full adder. And even though this is more complicated, you can see here, if you pay attention, this is just two half adders stuck together, and then an additional gate here to handle the carries. And functionally, this works the same as the half adder, except it also accepts a carry flag. And this carry flag is treated as an additional value to be added. So for example, this would be the equivalent of 0 plus 0 plus 0. We have the output of 0. If we have 0 plus 1 and then the carry flag is 1, it's treated as a simple addition between these three numbers. But the purpose of carry in is to interface with a carry out. If you want to add larger numbers together, all you have to do is duplicate all this in here, and then attach the carry out from here to the carry in of the one you just duplicated. Doing that in this simulator would make it a bit messy though, so instead I'm going to switch over to using just the full adder block, which is this symbol down here. So just imagine that this circuit here is represented by what's inside of this box. So this right here is the equivalent circuit. We have our two inputs A0 and B0, along with our carry in flag. But this is still just a 1-bit adder, and we want to add larger numbers. So to do that, we're going to copy everything from here, paste it, and then attach the carry out of this adder to the carry in of this adder. And here I've done that a couple more times, so now we have a 4-bit adder. So we have our A value here, which is 4 bits, and our B value in here, which is 4 bits, and the adders will add these numbers together. So if we do 1 plus 1, we have 2. Or if we have 1 plus 3, we have 4. And this right here is everything we've done so far, just simplified even further. So we can still do things like 1 plus 2 and get our result in decimal. So we have enough now to add numbers, but what if we want to subtract numbers? And you'll remember that this is an adder, it's not a subtractor. So this circuit here can only add numbers together. Fortunately, it's very simple to do subtraction only using addition. And this is because subtraction can be done by adding a negative number. And the method we use to do this is called 2's complement. And I'll show you a basic example of how this works. So let's say we want to have the number 6 and we want to subtract 4 from it. The first step is to invert the subtrahend. So take all these bits and flip them to what their opposite should be, and then add 1 using the carry flag. And now we have the result of 2. To give the computer the ability to invert the bits of the subtrahend, we're going to add in another gate, in this case an exclusive OR gate, which will allow the computer to toggle whether or not it wants to invert the subtrahend. So this right here is our new setup. Ignore this box right here, this is just for the simulator. But now the process of subtracting is basically the same as before, but now we have something in place to automatically invert the subtrahend. So same as before, I'm going to say we want to take 6 and subtract 4 from it. So we're going to select this bit right here, which will invert this subtrahend, and then click on here to add 1. And we have our 6 minus 4 equals 2. Now this might seem like a lot to only add 2 functions to the ALU, but what if I was to tell you that in terms of functionality, the ALU is almost finished? Let's take a look at the functions we've already covered. So we know for sure that the ALU can now add and subtract. But we've also added the ability to multiply and divide. This is because multiplication is just repeated addition, and division is just repeated subtraction. Most modern computers would have hardware acceleration for multiplication and division, but because we're focusing on keeping things as minimalist as possible, we can use software to emulate these functions. So cool, we have our 4 main arithmetic functions working, but we've also added another huge function, number comparison. When a program is running, we need the computer to be able to make decisions based on the context of the program and the memory. This making decisions capability is done almost entirely through comparing numbers together, such as greater than, less than, equals to, not equal, etc. All of these functions can be done just by using subtraction. But in order to do this, we need to add a few more components. Firstly, the ALU currently does not have a way to store the output of a computation. What we want is an area where the ALU can place the result of a function so that the computer can then use it later on. So to do this, we're going to be adding something called an accumulator hold register. This register will be placed at the output of the adders, and its job is to hold the result of a computation until it can be moved somewhere more permanent. But this register is also there to perform another important task, checking for the number 0. If all the bits inside the accumulator hold register are switched off, we know that the value it holds is 0. This is important when the computer is testing to see if two numbers are the same, because if we take any number and subtract it from itself, the output will be 0. But if the two numbers subtracted aren't the same, the hold register will not be 0. To check if all the bits in the register are off, we have a few options. Arguably, the best solution is to use a device called an 8-bit identity comparator. Basically, this takes 2 bytes and compares them together, outputting if the values are equal or not. This will be attached directly to the output of the hold register. The output of this comparator will then be sent to the control logic of the computer. Finally, we need to have something in place to store the carry flag. This is necessary because for some operations, we'll need to retain the carry flag while using the ALU logical functions. To do this, we're going to use a simple D-type flip-flop that connects to the carry flag output of the ALU. Now we're almost finished with the ALU. The next step is to add the logical functionality to the ALU. This will require rearranging some of the components we've already placed and adding a few new ones. So we'll save all that for the next video in this series.